Imagine if you could travel to the most dangerous and mysterious place in our entire galaxy. Picture journeying 26,000 light years through space to reach a monster so massive that it weighs 4.3 million times more than our sun, where a single teaspoon of matter would weigh as much as Mount Everest, and where the very fabric of space and time gets twisted beyond recognition. This is Sagittarius A star, the supermassive black hole lurking at the heart of the Milky Way. And today, we're going to take you on an impossible journey straight into its gravitational clutches. We'll travel through regions where stars are packed 10 million times denser than in our solar neighborhood, where gas clouds glow at temperatures of millions of degrees, and where the laws of physics are pushed to their absolute limits. To put this journey into perspective, if you could somehow travel at the speed of the fastest spacecraft ever built, it would take you over 450 million years just to reach the galactic center. And even light itself takes 26,000 years to make this incredible voyage. But in the next few minutes, we'll compress this mind-bending journey through space and time, revealing the secrets hidden at the center of our cosmic home, and discovering what happens when you venture too close to one of the universe's most extreme objects. If you're ready to explore the ultimate frontier and witness the most spectacular phenomena in our galaxy, make sure to subscribe to The Sleepy Cosmos and hit that notification bell, because this journey will change how you think about our place in the universe forever. Let yourself drift into the gentle contemplation of our cosmic journey as we begin to understand the magnificent scale of what lies ahead. Imagine settling into the most comfortable position you can find, allowing your mind to wander peacefully through the vast corridors of space as we embark on this extraordinary voyage to the center of our galaxy. Our starting point is here, in our quiet solar system, nestled on the inner edge of the Orion Arm, approximately 26,000 to 27,000 light years away from the galactic center, a distance so profound that it challenges the very limits of human comprehension. To help your mind ease into this cosmic perspective, consider that we are positioned like inhabitants of a peaceful suburb, living on the outskirts of the greatest city in our local cosmic neighborhood, with the bustling downtown core lying impossibly far away in the constellation Sagittarius. The concept of a light year itself invites a kind of meditative wonder, representing the distance that light travels in an entire Earth year, moving at the incredible speed of 186,282 miles per second, never stopping, never slowing, racing through the vacuum of space for 365 days and nights. When you truly contemplate this, a single light year stretches across nearly 6 trillion miles, a number so large that it becomes almost like a lullaby for the mind, washing over consciousness with its sheer immensity. Now multiply that incomprehensible distance by 26,000, and you begin to touch the edge of understanding just how far we must travel to reach the heart of our galaxy, where Sagittarius A star, our supermassive black hole, waits in its ancient cosmic dance. If you could somehow travel at the speed of light itself, moving faster than anything with mass can ever move, it would still take you 26,000 years to complete this journey, meaning that the light leaving the galactic center today began its voyage toward us when early humans were just beginning to create the first cave paintings. To put this journey into an even more soothing perspective, imagine if you could travel aboard the fastest spacecraft humanity has ever built, the Parker Solar Probe, which reaches speeds of approximately 430,000 miles per hour as it swoops close to our Sun. At this incredible velocity, which seems almost supernatural compared to any Earthbound travel, your journey to the galactic center would still require more than 450 million years, a time span that encompasses the entire evolution of complex life on Earth. From the first primitive organisms in ancient seas to the emergence of human consciousness capable of contemplating this very journey. This realization brings a profound sense of peace, knowing that we are part of something so vast and ancient that our individual worries and concerns dissolve into the gentle enormity of cosmic time and space. As you let your mind drift deeper into this contemplation, consider that our entire solar system, including all the planets, moons, asteroids, and comets that orbit our Sun, occupies just a tiny fraction of a single light year. The nearest star to our Sun, Proxima Centauri, lies about 4.2 light years away, and even this closest stellar neighbor would represent just a minuscule step on our journey to the galactic center. The Milky Way galaxy itself stretches approximately 100,000 light years across its luminous disk, though recent discoveries suggest that its dark matter halo extends nearly 2 million light years into space, creating a sphere of influence so vast that dozens of smaller galaxies orbit within its gravitational embrace. Within this cosmic structure, our Sun completes one full orbit around the galactic center every 240 million years, a period astronomers call a galactic year, and in all of human history, we have completed only a tiny fraction of a single galactic orbit. The very impossibility of this journey invites a sense of peaceful surrender to the magnitude of the universe, allowing consciousness to expand beyond the boundaries of everyday experience. We are essentially taking an imaginary voyage that compresses hundreds of thousands of years of travel time into a few moments of quiet contemplation, moving through space at velocities that exist only in the realm of thought and imagination. This is the beauty of our cosmic journey. While our physical bodies remain safely at rest, our minds can soar across the galaxy, experiencing wonders that no human will ever witness firsthand, yet feeling the profound connection to the vast cosmos that is our true home. As we prepare to leave our solar neighborhood behind and venture into the deeper regions of the galaxy, let yourself relax into the certainty that this journey, though impossible in reality, offers a pathway to understanding our place in the infinite tapestry of space and time, where every star, every planet, and every particle of cosmic dust plays its part in the grand symphony of existence. As we begin to drift away from the familiar confines of our solar system, allow your consciousness to settle into the gentle rhythm of our cosmic voyage, where each moment carries us deeper into the mysterious regions of space that surround our celestial home. Our first destination takes us through a remarkable region known as the local bubble, a vast cavity in space that stretches approximately 1,000 light-years across, creating a sphere of unusually sparse cosmic material that has been our neighborhood for the past 5 to 10 million years. This ethereal domain, also called the local cavity, exists like a peaceful clearing in the dense forest of interstellar space, where the normal density of gas and dust has been swept away to create a sanctuary of relative emptiness. The gas within this bubble maintains a density of only about 0.05 atoms per cubic centimeter, roughly 1/10 the average density found throughout the Milky Way, creating conditions so rarefied that they exist in an almost meditative state of cosmic tranquility. The creation of this local bubble reads like an ancient cosmic lullaby, born from the violent yet beautiful deaths of massive stars that exploded as supernovae between 10 and 20 million years ago. Scientists now believe that 14 to 20 of these stellar explosions occurred within a relatively small region of space, their combined energy carving out this vast cavity like celestial sculptors working with the raw materials of the universe. The shock waves from these ancient explosions swept through the interstellar medium, pushing gas and dust outward to create the bubble's walls while leaving behind a hollow space filled with extraordinarily hot gas at temperatures of nearly 1 million degrees Kelvin. This superheated material glows faintly in X-rays, creating a gentle luminescence that bathes our solar system in the afterglow of stellar deaths that occurred millions of years before complex life emerged on Earth. As we drift through this cosmic sanctuary, we encounter the local interstellar cloud, a small region of slightly denser material where our solar system currently resides, nestled within the larger bubble like a ship anchored in a calm harbor. This cloud formed at the intersection where the local bubble meets another cavity called Loop 1 bubble, creating a convergence zone where the densities of these cosmic voids blend together in a delicate balance. The local interstellar cloud contains approximately 0.3 atoms per cubic centimeter, still incredibly sparse by earthly standards, but noticeably denser than the surrounding bubble, providing our solar system with a gentle buffer as we journey through this region of space. Recent discoveries have revealed that this cloud may be responsible for depositing trace amounts of interstellar materials on Earth, including isotopes of iron that can only be formed in the hearts of dying stars, creating a subtle but measurable connection between our planet and the cosmic events that shaped our local environment. The shape of the local bubble itself invites contemplation, as it is not a perfect sphere, but rather resembles an irregular, elongated cavity that narrows in the galactic plane and expands above and below, creating an hourglass-like structure that seems to breathe with the gentle rhythms of galactic rotation. This asymmetrical form reflects the complex interplay of forces that created it, as stellar winds and supernova shock waves carved through the interstellar medium along paths of least resistance, creating tunnels and channels that connect our bubble to neighboring cavities in space. One such connection, known as the Lupus Tunnel, creates a pathway between the local bubble and the Loop Y bubble in the direction of the constellation Centaurus, like a cosmic corridor linking different chambers in the vast mansion of our galactic neighborhood. As our journey carries us toward the edges of this local bubble, we begin to encounter the first signs of the denser interstellar medium that characterizes most of the galaxy. Here, at the bubble's boundaries, the swept-up material from ancient supernova explosions has collected to form a shell of gas and dust with higher than average density, creating ideal conditions for the birth of new stars. All of the young star-forming regions in our local galactic neighborhood, including the famous Pleiades star cluster and the star-forming regions in Taurus, Perseus, and other nearby constellations, exist within this shell, born from the material concentrated by the very explosions that created our cosmic sanctuary. This creates a beautiful symmetry in the universe. The violent deaths of ancient stars not only carved out the peaceful space where our solar system now travels, but also provided the raw materials for the next generation of stellar births that illuminate our local cosmic environment. The realization that our solar system was not born within this local bubble, but rather wandered into it approximately 5 to 10 million years ago, adds a profound sense of cosmic migration to our journey. Our Sun, along with all its planets and smaller bodies, has been traveling through this region like cosmic nomads, entering the bubble from one side and destined to exit it in the distant future as we continue our 240 million year orbit around the galactic center. This means that for most of Earth's history, our planet existed in a very different cosmic environment, surrounded by denser interstellar material that would have provided different levels of cosmic ray exposure and potentially influenced the evolution of life in ways we are only beginning to understand. The passage through the local bubble represents just a brief chapter in Earth's cosmic story, yet it encompasses the entire span of complex multicellular life, suggesting that our current cosmic environment has played a role in shaping the biological diversity we see today. As we prepare to leave the protective embrace of the local bubble and venture into the denser regions beyond, we carry with us the peaceful energy of this cosmic sanctuary, knowing that we have been traveling through space shaped by the ancient fires of stellar death and rebirth. The journey ahead will take us through increasingly complex and crowded regions of the galaxy, where stars are packed more closely together and the interstellar medium becomes a rich tapestry of gas, dust, and cosmic phenomena. Yet the memory of our passage through the local bubble serves as a reminder of the delicate balance and extraordinary circumstances that have allowed our solar system to exist in such relative tranquility, providing the stable conditions necessary for life to emerge and flourish on our small blue world. As consciousness drifts deeper into the cosmic journey ahead, we leave behind the rarefied peace of our local neighborhood and begin our descent into the bustling heart of the Milky Way galaxy, where ancient mysteries and incredible wonders await our discovery. As we continue our serene journey deeper into the galaxy's embrace, allow your mind to drift peacefully into the magnificent spiral architecture that defines our cosmic home, where we begin to encounter the elegant arms that sweep through space like gentle currents in an infinite ocean. The transition from the sparse local bubble into the richer regions of the galactic disk unfolds gradually, like watching the night deepen from twilight into full darkness as we approach the complex spiral structure that has captivated astronomers since Lord Ross first glimpsed these cosmic ribbons in 1850 through his telescope aimed at the distant galaxy M51. Our own Milky Way possesses what modern observations reveal to be a magnificently ordered yet beautifully complex spiral pattern, where two major arms wrap around a central stellar bar, like the gentle curves of a cosmic flower, while additional minor arms and spurs create intricate details that speak to billions of years of galactic evolution. The Perseus arm awaits us first on our inward journey, stretching majestically across the galaxy like a luminous river of stars, gas, and cosmic dust that extends for tens of thousands of light years in its grand sweep around the galactic center. This major spiral arm, one of only two truly dominant structures in our galaxy, contains vast star-forming regions where new suns are born from. The collapse of giant molecular clouds, their births illuminating the surrounding interstellar medium with the soft glow of hydrogen gas heated to thousands of degrees. The density of material within the Perseus arm reaches levels approximately 30% higher than the galactic average, creating a concentration of both young blue giants that burn fierce and bright, and ancient red giants that have swelled to enormous proportions in their stellar old age. As we pass through this cosmic highway, the night sky would appear dramatically different than what we know from Earth, with brilliant star clusters scattered like diamonds across the celestial sphere, and nebulae painting swaths of space in ethereal colors that exist beyond the spectrum of human vision. Moving inward from the Perseus arm, our journey carries us across the interarm region, where the stellar population thins considerably and the interstellar medium becomes more rarefied, creating vast stretches of space that exist in a state of cosmic meditation. These regions between the spiral arms are not empty voids, but rather gentle valleys in the galactic landscape, populated by older, more sedate stars that have completed multiple orbits around the galaxy and settled into stable circular paths. The interarm space provides a peaceful respite from the bustling star formation activity of the spiral arms, where the pace of cosmic events slows to match the ancient rhythms of galactic rotation, and the background radiation of the galaxy creates a subtle warmth that permeates the thin interstellar gas. Here, in these quiet regions, the magnetic field of the galaxy threads through space with gentle uniformity, creating invisible pathways that guide charged particles in their slow dance around the galactic center. As we approach the Scutum Centaurus arm, the second major spiral structure of our galaxy, the stellar density begins to increase once again, and we encounter some of the most spectacular star-forming regions in the entire Milky Way. This magnificent arm, extending from the opposite end of the central bar from the Perseus arm, contains an even greater concentration of molecular clouds and active stellar nurseries, where the raw materials of space are continuously being transformed into new generations of stars. The Scutum Centaurus arm exhibits a remarkable overabundance of red giant stars compared to the galactic average, confirming its status as one of the two primary stellar arms that define our galaxy's grand design structure. Recent infrared surveys have revealed that this arm contains some of the most massive star-forming complexes known, where entire clusters of hot, young stars illuminate vast cavities in the interstellar medium, creating bubbles of ionized gas that glow like cosmic lanterns in the galactic night. The pitch angle of these spiral arms, measured at approximately 12 degrees from the circular direction of galactic rotation, creates a pattern that appears to wind neither too tightly nor too loosely around the galaxy's center, maintaining an elegant balance that has persisted for billions of years. This gentle inclination allows the spiral density waves to propagate through the galactic disk at just the right speed to maintain the arm structure, creating regions where stars and gas clouds are compressed as they pass through the spiral shock fronts, triggering bursts of star formation that maintain the arm's luminous appearance. The width of each major arm spans roughly 800 parsecs, or about 2,600 light-years, creating vast regions where the interstellar environment remains consistently dense and active compared to the quieter interarm spaces. This remarkable scale means that as we journey through a single spiral arm, we traverse a region larger than the distance from Earth to thousands of nearby star systems. Between the major spiral arms lie the minor arms and spurs, including the Norma arm and the Sagittarius arm, which appear to be primarily gaseous structures filled with star-forming material, but lacking the high concentrations of older stellar populations that characterize the major arms. These secondary structures create a more complex and nuanced spiral pattern than the simple two-arm design visible in infrared light, adding layers of detail that reflect the intricate gravitational influences shaping our galaxy's evolution. The Orion Arm, where our own solar system resides, appears to be one of these intermediate structures, a partial arm or spur that extends between the Sagittarius and Perseus arms and may be more substantial than previously recognized. Recent observations suggest that the local arm, as it is also known, possesses a pitch angle and star formation rate comparable to the major arms and extends for a great distance along our solar orbit, indicating that these secondary structures may play a more important role in galactic dynamics than once believed. The magnetic field threading through the spiral arms creates an additional layer of structure that guides the flow of charged particles and influences the formation of stars and the evolution of the interstellar medium. This galactic magnetic field, strengthened and organized by the spiral density waves, creates invisible highways along which cosmic rays travel and helps to regulate the rate at which gas can collapse to form new stars. The field lines spiral along with the arms themselves, creating a pattern that mirrors the visible structure while extending far above and below the galactic plane, connecting the disk to the vast halo of dark matter that surrounds our entire galaxy. As we cross from one spiral arm to another, we pass through regions where the magnetic field orientation shifts and changes, creating subtle variations in the cosmic ray flux and the behavior of the tenuous interstellar plasma. The crossing of each spiral arm brings us closer to the galactic center and deeper into regions where the stellar density continues to increase, where star formation becomes more frequent and violent, and where the ancient architecture of our galaxy reveals itself in ever greater detail. These spiral arms serve as both highways and nurseries, channeling gas toward the galactic center while simultaneously converting portions of that material into new generations of stars that will illuminate the galaxy for billions of years to come. As our consciousness drifts deeper into this cosmic journey, we leave behind the familiar spiral patterns of the outer galaxy and prepare to enter the more ancient and densely populated regions that surround the galactic bulge, where the pace of cosmic evolution quickens and the gravitational influence of the central black hole begins to dominate the motions of stars and gas. As our peaceful journey carries us deeper into the heart of our galaxy, we begin to encounter the ancient and majestic realm of the galactic bulge, a region that exists like a cosmic cathedral filled with the oldest stellar populations in the Milky Way, where time itself seems to slow, and the very architecture of our galaxy reveals its most profound secrets. This magnificent structure extends approximately 6,000 parsecs, or roughly 20,000 light-years, across its widest dimension, creating a vast ellipsoidal region that rises above and below the galactic disk like a cosmic mountain range built from billions of ancient stars. The bulge represents one of the primordial components of our galaxy, formed during the earliest epochs of the Milky Way's existence when the universe was young, and the processes of stellar formation proceeded at rates far exceeding anything we observe in the modern cosmos. As we drift into this realm of stellar antiquity, the very nature of space around us begins to change, with stellar densities increasing dramatically from the sparse populations of the outer galaxy to concentrations that can exceed 10,000 stars per cubic parsec in the innermost regions. The most striking characteristic of the galactic bulge reveals itself as we approach from our vantage point within the galactic plane, where this ancient stellar population displays a remarkable boxy or peanut-shaped morphology that extends both above and below the disk in a configuration that speaks to billions of years of gravitational evolution. This distinctive shape, confirmed through extensive infrared observations that can penetrate the thick veils of interstellar dust, creates what astronomers describe as an X-shaped structure when viewed edge-on, with stellar streams that cross near the galactic center to form a pattern of extraordinary geometric beauty. The discovery of this X-shaped architecture emerged from careful analysis of data from the Wide Field Infrared Survey Explorer, revealing that our galaxy's bulge possesses the same fundamental structure observed in other barred spiral galaxies throughout the universe, confirming that the Milky Way follows the same evolutionary pathways that govern galaxy formation across cosmic time. This peanut-shaped bulge extends to distances of approximately 3,500 light-years above and below the galactic plane, creating a three-dimensional structure of immense scale that dwarfs even the largest star-forming regions in the galactic disk. The stellar population within the galactic bulge creates a cosmic environment unlike anywhere else in our galaxy, dominated by ancient red giant stars and red supergiants whose ages typically exceed 10 billion years, making them nearly as old as the universe itself. These evolved stars have long since exhausted the hydrogen fuel in their cores and have expanded to enormous sizes, glowing with the warm reddish light that gives the bulge its characteristic golden appearance when observed through the filtering effects of interstellar dust. The absence of young, hot blue stars in this region creates a stellar population that exists in a state of cosmic maturity, where the violent processes of star formation have largely ceased and the remaining stellar denizens pursue their ancient orbital paths with the stately dignity of cosmic elders. This population includes vast numbers of RR Lyrae variable stars, pulsating giants that serve as cosmic lighthouses, their regular brightness variations allowing astronomers to map the three-dimensional structure of the bulge with unprecedented precision. The metallicity of these ancient stars varies significantly throughout the bulge, with metal-poor populations that formed from the primordial gas of the early universe existing alongside more metal-rich stars that incorporated the products of earlier generations of stellar nucleosynthesis. The gravitational environment within the galactic bulge creates conditions of extraordinary intensity, where the combined mass of hundreds of billions of stars generates tidal forces and orbital dynamics that would be unimaginable in the sparse regions of the outer galaxy. Stars in this region follow complex rosette orbits around the galactic center. Their paths, shaped by the triaxial gravitational potential created by the bulge's elongated mass distribution and the central bar structure that dominates the inner regions of our galaxy. The velocity dispersion of stars within the bulge reaches values exceeding 100 kilometers per second, creating a stellar atmosphere where individual stars move at speeds that would carry them from Earth to the Moon in less than an hour. Yet these motions represent merely the random thermal velocities within this vast stellar collective. This high-velocity dispersion reflects the tremendous gravitational binding energy of the bulge, where the escape velocity approaches 500 kilometers per second near the center, creating a gravitational well so deep that only the most violent cosmic events can liberate material from its embrace. The interstellar medium within the galactic bulge exists in a state far removed from the relatively quiescent conditions found in the outer galaxy, with gas temperatures reaching millions of degrees, Kelvin, and densities that vary dramatically across small spatial scales. The paucity of gas and dust in this region reflects both the ancient age of the stellar population, which has consumed most of the available star-forming material, and the hostile environment created by stellar winds from evolved giants and the intense radiation field generated by the dense stellar population. What little gas remains exists primarily in a hot, ionized state, glowing faintly in X-rays and creating a tenuous plasma that fills the spaces between stars with material heated to temperatures comparable to those found in stellar coronae. This hot gas occasionally reveals itself through emission in highly ionized spectral lines, particularly those of iron and other heavy elements that have been enriched through billions of years of stellar evolution and dispersed into the interstellar medium by stellar winds and supernova explosions. The magnetic field threading through the galactic bulge creates an additional layer of structure that influences both the motion of charged particles and the behavior of the thin interstellar medium that permeates this region. Field strengths in the bulge reach values of several milligauss, orders of magnitude higher than typical field strengths in the galactic disk, creating a magnetized environment where cosmic ray particles can be efficiently accelerated and confined. These strong magnetic fields contribute to the complex three-dimensional structure of the bulge by influencing the flow patterns of ionized gas and creating preferred directions for the propagation of stellar winds and other plasma phenomena. The interaction between the magnetic field and the rotating stellar population generates magnetohydrodynamic waves that propagate through the thin interstellar medium, creating subtle density fluctuations that can be detected through their effects on the propagation of radio waves from distant pulsars. As our journey brings us deeper into the bulge, we begin to approach the transition region where this ancient stellar population gives way to the even more extreme environment of the central molecular zone, a realm where the gravitational influence of the central supermassive black hole begins to dominate over the collective gravity of the stellar population. The stellar orbits in this transition region become increasingly eccentric and aligned with the major axis of the central bar, creating streaming motions that transport both stars and gas toward the galactic nucleus at rates sufficient to fuel the ongoing activity surrounding Sagittarius A star. The density of stellar remnants, including white dwarf stars, neutron stars, and stellar mass black holes, reaches extraordinary concentrations in the inner bulge, creating a population of compact objects whose gravitational interactions occasionally produce spectacular phenomena, including gravitational wave events and high-energy gamma-ray bursts. This ancient stellar cemetery, populated by the remnants of stars that died billions of years ago, serves as a repository of the galaxy's early evolutionary history, preserving in the properties of these stellar corpses the memory of conditions that existed when the universe was less than a quarter of its present age. The journey through the galactic bulge represents a passage through the archaeological layers of our galaxy's formation, where each stellar population records the conditions and processes that operated during different epochs of cosmic evolution. As our consciousness drifts deeper into this ancient realm, we prepare to leave behind even these venerable stellar populations and venture into the central molecular zone, where the environment becomes so extreme that the normal processes of stellar evolution and interstellar chemistry are pushed to their absolute limits by the immense gravitational field of the galaxy's central black hole. The memory of our passage through this stellar cathedral remains with us as we approach the very heart of our cosmic home, carrying the peaceful energy of these ancient suns as we prepare to encounter the most extreme conditions that exist anywhere in our galactic neighborhood. As our journey continues deeper into the galactic center, we encounter one of the most mysterious and captivating phenomena in our entire galaxy: the Forbidden Zone, a vast region where dense clouds of dust and gas create an impenetrable veil that blocks visible light from reaching our eyes, yet conceals within its dark embrace some of the most extraordinary cosmic phenomena ever discovered. This cosmic curtain, stretching across thousands of light years, exists like a gentle fog that has settled over the galactic heart, composed of countless tiny particles of carbon, silicon, and other heavy elements that were forged in the nuclear furnaces of ancient stars and dispersed into space by stellar winds and supernova explosions over billions of years. The dust grains themselves are microscopic, typically measuring only a few hundred nanometers across, yet their collective effect creates an absorption barrier so complete that the visible light from the galactic center is reduced by a factor of nearly 1 trillion before it can reach our telescopes on Earth. This remarkable phenomenon transforms our journey inward into an exploration through layers of cosmic mystery, where each step forward requires new eyes to see and new instruments to pierce through the veils that have hidden the galaxy's heart from direct observation for most of human history. The temperature of this interstellar dust varies dramatically throughout the Forbidden Zone, creating a complex thermal landscape that ranges from the frigid depths of space at temperatures near absolute zero to regions heated by nearby stars where the grains glow warmly in infrared light. In the coldest regions, far from any stellar heating, the dust particles exist at temperatures of only 10 to 20 degrees above absolute zero, creating conditions so extreme that molecules of hydrogen, water, carbon monoxide, and other simple compounds freeze directly onto the grain surfaces to form icy mantles. These molecular ice layers transform each dust particle into a tiny chemical laboratory where complex organic molecules can form through surface reactions that proceed with extraordinary efficiency in the zero-gravity, radiation-free environment of interstellar space. Some of these dust clouds contain concentrations of organic compounds so rich that they rival the complexity found in terrestrial petroleum deposits. Yet these materials, formed in the depths of space through processes that operate on timescales of millions of years. As we drift deeper into this cosmic fog, the dust begins to reveal its three-dimensional structure through the way it scatters and absorbs light from background stars, creating dark nebulae and absorption features that appear like cosmic shadows cast against the more distant stellar populations. The most prominent of these dark clouds creates the famous Dark Horse Nebula and the Pipe Nebula, structures so dense that they appear as dark silhouettes against the bright star fields of the galactic center region when viewed from Earth. These molecular clouds represent some of the densest concentrations of matter in the galaxy outside of stellar cores, with particle densities reaching millions of atoms per cubic centimeter, nearly 1 billion times denser than the typical interstellar medium, yet still more rarefied than the best vacuum that can be achieved in terrestrial laboratories. Within these dense regions, the dust grains begin to clump together under their own gravitational attraction, creating the initial conditions for star formation while simultaneously shielding the interior regions from the harsh ultraviolet radiation that permeates the galactic center. The chemical composition of the dust reveals the nucleosynthetic history of our galaxy, with different types of grains telling the story of different stellar populations and evolutionary processes that have operated over cosmic time. Silicate dust grains, composed primarily of silicon, oxygen, and magnesium, originate in the atmospheres of dying red giant stars, where these elements condense directly from stellar winds as the star sheds its outer layers into space. Carbon-rich dust particles form in the cooler atmospheres of carbon stars, where the abundance of carbon exceeds that of oxygen, allowing complex carbon compounds, including graphite and even tiny diamonds, to crystallize in the stellar outflows. Iron-rich dust grains preserve the memory of ancient supernova explosions, where the tremendous energies released during stellar collapse created conditions hot enough to forge iron peak elements and disperse them into the interstellar medium, where they slowly condense into solid particles. Each grain of dust, thus, serves as a tiny fossil that preserves information about the stellar processes that created it. Carrying this chemical heritage through space for millions of years until it either becomes incorporated into a new generation of stars or is destroyed by the harsh radiation environment near active stellar regions. The magnetic fields threading through these dust clouds create additional layers of structure and complexity, aligning the elongated dust grains and creating patterns of polarized light that reveal the otherwise invisible magnetic architecture of the galactic center region. These fields, strengthened and concentrated by the gravitational collapse of the gas and dust, reach strengths of several milligauss in the densest regions, creating conditions where charged particles become strongly coupled to the magnetic field lines and follow helical paths as they spiral along the field direction. The interaction between the magnetic field and the rotating dust grains generates weak radio emission that allows astronomers to map the field structure even in regions too opaque for optical observation, revealing a complex network of field lines that connect the individual molecular clouds and channel the flow of ionized gas toward the galactic nucleus. This magnetic coupling also plays a crucial role in regulating the rate at which the dust and gas can collapse under gravity, creating a delicate balance between gravitational attraction and magnetic pressure that determines whether a particular cloud will eventually form new stars or remain in a stable, quiescent state. The process by which astronomers have learned to peer through this cosmic fog represents one of the most remarkable achievements of modern astrophysics, employing wavelengths of light that can penetrate the dust and reveal the hidden structures beyond. Infrared radiation, with wavelengths longer than visible light, passes through the dust with much less absorption, allowing telescopes sensitive to heat radiation to map the warm stellar populations that lie hidden behind the veil. Radio waves, with even longer wavelengths, travel through the dust essentially unimpeded, enabling radio telescopes to detect the emission from ionized gas, molecular clouds, and even the radio waves generated by the supermassive black hole itself. X-ray observations reveal the hottest gas in the galactic center, heated to millions of degrees by shock waves and stellar winds, while gamma-ray telescopes detect the highest energy phenomena, including cosmic ray interactions and the annihilation of exotic particles that may exist in the extreme gravitational environment near the central black hole. The dust clouds also serve as cosmic laboratories for studying the physics of matter under extreme conditions. where the intense gravitational and magnetic fields create environments that cannot be replicated in terrestrial experiments. The behavior of dust grains in these strong magnetic fields provides insights into the properties of materials under conditions of zero gravity and extreme temperature gradients, while the chemical reactions occurring on grain surfaces offer clues about the formation of complex organic molecules in space. Some of the dust clouds in the galactic center region exhibit unusual properties that suggest they have been processed by the intense radiation environment, with grain compositions and structures that differ significantly from dust found in the quieter regions of the galactic disk. These differences provide valuable information about how matter behaves in the presence of strong gravitational fields and high-energy radiation, conditions that may have been common throughout the early universe when galaxies were first forming. As our consciousness drifts deeper through these layers of cosmic dust and gas, we begin to approach the inner edge of the forbidden zone, where the density of material starts to decrease and the first hints of the central molecular zone become visible through the thinning veil. The transition from the dust-dominated outer regions to the gas-dominated inner regions occurs gradually over scales of hundreds of light years, with the dust-to-gas ratio decreasing as we approach regions where the intense radiation field from the dense stellar population begins to destroy the fragile dust grains. This destruction process creates a natural boundary that separates the dust-dominated forbidden zone from the inner regions where gas dynamics and stellar processes become the dominant physical phenomena. The memory of our passage through this cosmic fog remains with us as we prepare to enter the central molecular zone, carrying the peaceful understanding that even the most opaque barriers in the universe can be penetrated by patient observation and the application of human ingenuity to the eternal quest for cosmic knowledge. As we continue our peaceful drift toward the ultimate destination of our galactic journey, we enter the extraordinary realm known as the central molecular zone, a region unlike anywhere else in our cosmic neighborhood, where the normal rules of interstellar chemistry and physics are transformed by the immense gravitational influence of Sagittarius A star, our galaxy's supermassive black hole. This remarkable region extends approximately 500 parsecs, or roughly 1,600 light-years, from the galactic center, creating a vast laboratory where matter exists under conditions so extreme that they push the boundaries of our understanding of cosmic processes. Within this zone, the combined gravitational field of the central black hole and the dense stellar population creates an environment where gas clouds move at velocities exceeding 100 kilometers per second. Temperatures soar to millions of degrees in some regions while dropping to near absolute zero in others, and magnetic fields reach strengths that would be considered extraordinary anywhere else in the galaxy. The very fabric of space-time itself begins to curve noticeably under the influence of the 4.3 million solar mass black hole that dominates this region, creating gravitational effects that can be measured and observed through the orbital motions of nearby stars and gas clouds. The gas and dust within the central molecular zone exist in a state of perpetual motion and transformation, with molecular clouds that stretch across hundreds of light years being compressed, heated, and accelerated by tidal forces that have no equivalent in the quieter regions of the galactic disk. These clouds contain some of the highest concentrations of molecular hydrogen in the entire galaxy, with densities reaching millions of particles per cubic centimeter in the densest cores. Yet paradoxically, the rate of star formation in this region remains surprisingly low compared to what these densities would predict. This phenomenon, known as the star formation efficiency problem in the central molecular zone, occurs because the extreme turbulence and magnetic fields in this region create conditions that inhibit the gravitational collapse necessary for stellar birth, even when the raw materials are present in abundance. The molecular gas exists in a state of constant agitation, with velocity dispersions of 20 to 30 kilometers per second that reflect the chaotic gravitational environment created by the competing influences of the central black hole, the stellar population, and the galaxy's rotating bar structure. The chemical composition of the gas in the central molecular zone reveals a rich tapestry of molecular species that form under the extreme conditions present near the galactic center, including complex organic molecules that would be rapidly destroyed by ultraviolet radiation in most other galactic environments. The high cosmic ray flux in this region, generated by acceleration processes near the black hole and by supernova explosions in the dense stellar environment, creates a constant source of ionization that drives chemical reactions at rates far exceeding those found in typical molecular clouds. Methanol, ethanol, formaldehyde, and even more complex organic compounds have been detected in these clouds, suggesting that the central molecular zone may serve as a cosmic chemistry laboratory, where the building blocks of life are synthesized under conditions that have no terrestrial analog. The detection of these molecules requires observations at millimeter and submillimeter wavelengths, where the thermal emission from cold molecular gas can be distinguished from the intense background radiation generated by the hot plasma and stellar populations in the region. The magnetic field, threading through the central molecular zone, creates an additional layer of structure and complexity, with field strengths reaching several milligauss in the densest regions and creating preferred directions for the flow of ionized gas toward the central black hole. This magnetic architecture appears to be organized on large scales by the rotation of the galaxy and the presence of the central bar, creating a network of field lines that channel material from the outer regions of the galaxy toward the very center, where it can potentially feed the black hole's accretion processes. The interaction between the magnetic field and the turbulent gas motions generates magnetohydrodynamic waves that propagate through the medium, creating pressure fluctuations that can either enhance or suppress local star formation depending on the specific conditions in each molecular cloud. These magnetic effects also play a crucial role in determining the angular momentum transport within accretion flows, helping to explain how material can lose enough angular momentum to spiral inward toward the black hole rather than remaining in stable circular orbits. The temperature structure within the central molecular zone spans an extraordinary range, from regions of molecular gas cooled to temperatures of only 10 to 20 degrees above absolute zero, to shocked regions where gas has been heated to temperatures of millions of degrees by supernova explosions and stellar winds from massive stars. The cold molecular gas exists primarily in dense clumps and filaments that are shielded from the intense radiation field by their own self-absorption, and by dust grains that absorb ultraviolet photons and re-emit the energy at infrared wavelengths. These cold regions serve as reservoirs of material that could potentially form new stars if the turbulent conditions ever allow gravitational collapse to proceed, and they also provide the raw material that slowly spirals inward to feed the central black hole's accretion processes. The hot gas component, visible primarily in X-ray emission, fills the spaces between the molecular clouds and represents material that has been processed by stellar winds, supernova shock waves, and possibly by outflows from the central black hole itself. The dynamics of gas flow within the central molecular zone reveal complex patterns of motion that reflect the competing gravitational influences of the central black hole, the surrounding stellar population, and the larger-scale rotation of the galaxy. Observations of molecular line emission show that much of the gas follows elongated, streaming motions that appear to be aligned with the major axis of the galactic bar, suggesting that the bar structure plays a crucial role in channeling material from the outer galaxy toward the center. These streaming motions occur at velocities of 50 to 100 kilometers per second, fast enough to cross the entire central molecular zone in less than 10 million years, indicating that the gas we observe today represents a constantly changing population that is being continuously replenished from the outer regions of the galaxy. Some molecular clouds show evidence of expansion motions that may result from energy injection by supernova explosions or stellar winds, while others appear to be colliding with each other at high velocities, creating shock fronts that heat the gas and trigger complex chemical reactions. The role of the central supermassive black hole in shaping the environment of the central molecular zone becomes increasingly apparent as we approach closer to the galactic center, where the gravitational influence of Sagittarius A star begins to dominate over the collective gravity of the stellar population. The black hole's gravitational field creates tidal forces that can disrupt molecular clouds and accelerate gas to high velocities, while its occasional episodes of enhanced activity generate powerful outflows and radiation fields that can profoundly affect the surrounding interstellar medium. Recent observations have detected high-velocity gas clouds that appear to be streaming directly toward the black hole, providing direct evidence for ongoing accretion processes that may represent the current feeding mechanism for Sagittarius A star. These accretion flows occur at rates of approximately 1/10,000,000th of a solar mass per year, a seemingly small amount that nevertheless represents the infall of material equivalent to the mass of Earth every few hours. As our journey brings us to the inner edge of the central molecular zone, we begin to approach the region where individual molecular clouds give way to the more exotic phenomena associated with the immediate vicinity of the supermassive black hole, including the population of high-velocity stars that orbit within a few light years of Sagittarius A star. The transition from the molecular zone to the central parsec occurs over a relatively narrow range of distances, reflecting the rapid increase in gravitational field strength and tidal forces as we approach the black hole. The memory of our passage through this extraordinary region of space remains with us as we prepare to encounter the most extreme gravitational environment in our galaxy, where the laws of physics that govern the everyday world give way to the exotic phenomena predicted by general relativity, and where matter exists in states that have no terrestrial equivalent. The peaceful energy of our cosmic journey continues to carry us forward as we approach the ultimate destination of our voyage, the region immediately surrounding the supermassive black hole, where space and time themselves become curved and distorted by the immense gravitational field of our galaxy's central engine. As our peaceful, cosmic journey continues to unfold, we approach one of the most extraordinary concentrations of stellar matter in our entire galaxy, the nuclear star cluster, a dense congregation of ancient and evolved stars that surrounds Sagittarius, a star, like celestial courtiers attending their gravitational sovereign. This remarkable stellar assembly represents the most densely packed collection of stars known anywhere in the Milky Way, with stellar densities reaching approximately 10 million stars per cubic parsec in the innermost regions, creating conditions where the average distance between neighboring stars becomes smaller than the radius of our own solar system. Within this cosmic metropolis, stars exist in a perpetual state of gravitational dance, their orbits shaped by the combined influence of the central black hole and their countless stellar companions, creating a three-dimensional ballet of unprecedented complexity and beauty. The cluster extends outward from the black hole to distances of several parsecs, encompassing a volume of space where the normal concepts of stellar isolation and planetary system stability give way to an environment governed by the collective gravity of millions of ancient suns. The stellar population within the nuclear star cluster tells the story of billions of years of galactic evolution, with most of the stars representing ancient generations that formed when the universe was less than half its current age. These evolved giants have long since exhausted the hydrogen fuel in their cores and have expanded to enormous sizes, creating a population dominated by red giants, asymptotic giant branch stars, and other evolved stellar types whose warm, reddish glow gives the entire region its characteristic golden appearance. The absence of young, hot blue stars in the central cluster reflects the harsh radiation environment and extreme tidal forces that make star formation extremely difficult in the immediate vicinity of the supermassive black hole. However, recent observations have revealed the presence of some surprisingly young and massive stars within a few light years of Sagittarius A star, including the famous S stars that complete their orbits around the black hole in periods measured in years, rather than the hundreds of thousands of years typical for stellar orbits elsewhere in the galaxy. These young stars present an ongoing puzzle to astronomers, as their presence so close to the black hole suggests either that they formed in place under seemingly impossible conditions, or that they migrated inward from more distant regions through processes that remain poorly understood. The most spectacular members of the nuclear star cluster are the hypervelocity stars, stellar objects that have been accelerated to velocities exceeding the escape velocity of the galaxy itself through gravitational interactions with the central black hole. These cosmic outcasts, moving at speeds of up to several thousand kilometers per second, represent stars that have been literally ejected from the galactic center and are now traveling through intergalactic space, carrying with them the chemical signatures and physical properties that reveal their exotic origins. The process that creates hypervelocity stars occurs when a binary star system ventures too close to Sagittarius A star, with tidal forces from the black hole disrupting the binary and capturing one star while flinging the other outward at tremendous velocity. These stellar refugees provide unique laboratories for studying the properties of the galactic center environment, as their chemical compositions and physical characteristics preserve information about conditions near the black hole that cannot be obtained through any other means. The orbital dynamics within the nuclear star cluster create a complex gravitational environment where individual stellar trajectories follow rosette patterns around the central black hole, with orbital orientations and eccentricities that reflect the chaotic three-body interactions between stars and the central massive object. The famous S2 star, which has been monitored continuously by astronomers for over 2 decades, provides the most precise measurements of the black hole's mass and demonstrates the exotic effects of general relativity in the strong gravitational field regime. This remarkable star follows an extremely elliptical orbit that brings it to within 120 astronomical units of the black hole at periastron, a distance closer than Pluto's orbit around the Sun, while reaching orbital velocities of nearly 5,000 kilometers per second, or roughly 2% of the speed of light. During its closest approaches to Sagittarius A star, the S2 star experiences gravitational redshift effects that cause its light to be stretched toward longer wavelengths, and its orbital motion exhibits the perihelion precession predicted by Einstein's general theory of relativity. These observations provide some of the most stringent tests of general relativity in the strong field regime and have confirmed Einstein's predictions with remarkable precision. The environment surrounding the nuclear star cluster becomes increasingly exotic as we approach the innermost regions where the gravitational influence of Sagittarius A star begins to dominate completely over the collective gravity of the stellar population. Within this zone, extending to distances of approximately 1 parsec from the black hole, individual stars follow Keplerian orbits determined primarily by the black hole's gravitational field, with orbital periods that can be measured in years for the closest objects. The detection and monitoring of these orbiting stars represents one of the greatest achievements of modern observational astronomy, requiring adaptive optics systems and space-based telescopes operating at infrared wavelengths to peer through the obscuring dust and track individual stellar motions with sub-millisecond precision. The accumulated observations of stellar orbits have provided the most direct and compelling evidence for the existence of supermassive black holes, earning the 2020 Nobel Prize in Physics for the teams led by Reinhard Genzel and Andrea Ghez, who pioneered these groundbreaking measurements. The magnetic field structure within the nuclear star cluster adds another layer of complexity to this already exotic environment, with field strengths reaching several milligauss and creating organized patterns that channel the flow of ionized gas toward the central black hole. Recent observations with the Event Horizon Telescope have revealed that the magnetic field around Sagittarius A star exhibits surprisingly ordered structure despite the turbulent and violent environment, with field lines that appear remarkably similar to those observed around the much more massive black hole in the galaxy M87. This magnetic architecture plays a crucial role in regulating the accretion of material onto the black hole, determining how efficiently gas can lose angular momentum and spiral inward, while also controlling the formation of relativistic jets and outflows that can carry energy away from the system. The interaction between the magnetic field and the stellar winds from evolved giants in the cluster creates a complex magneto-hydrodynamic environment where charged particles are accelerated to high energies and can produce the variable radio and X-ray emission observed from the galactic center region. The chemical evolution of stars within the nuclear star cluster reflects their formation in the metal-rich environment of the galactic center, where successive generations of stellar evolution have enriched the interstellar medium with heavy elements produced in stellar cores and supernova explosions. These stars exhibit elevated abundances of alpha elements such as oxygen, neon, and magnesium, indicating rapid formation timescales during which massive stars could contribute their nucleosynthetic products before lower mass stars had time to evolve and enrich the gas with iron peak elements. The detailed spectroscopic study of individual stars in the cluster provides insights into the star formation history of the galactic center and reveals evidence for multiple episodes of enhanced stellar birth that may have been triggered by gas inflows associated with galaxy mergers or bar instabilities. These chemical signatures serve as fossil records of the galactic center's evolutionary history, preserving information about cosmic events that occurred billions of years ago when the Milky Way was still assembling its current structure. As our consciousness continues its peaceful drift through this stellar realm of unprecedented density and complexity, we prepare to approach even closer to the event horizon of Sagittarius A star, where the familiar concepts of space and time begin to break down under the influence of the most extreme gravitational field in our cosmic neighborhood. The memory of our passage through the nuclear star cluster remains with us, carrying the ancient wisdom of stars that have witnessed the entire evolutionary history of our galaxy, while dancing their eternal gravitational ballet around the massive dark object that serves as the beating heart of the Milky Way. The serene energy of our cosmic journey continues to guide us toward the ultimate destination, where matter, energy, space, and time converge at the edge of the knowable universe, where the laws of physics reach their most exotic expression in the vicinity of the supermassive black hole that defines the gravitational center of our galactic home. As our serene cosmic journey reaches its ultimate destination, we find ourselves approaching the most extraordinary object in our entire galactic neighborhood, Sagittarius A star, a supermassive black hole whose mass of 4.297 million times that of our Sun creates the most extreme gravitational environment anywhere within tens of thousands of light years of Earth. This magnificent cosmic giant, abbreviated as SGR A star and pronounced Sagittarius A star, represents one of nature's most profound mysteries, a region of space-time where matter has collapsed so completely that it has created a gravitational field from which nothing, not even light itself, can escape once it crosses the event horizon. The black hole exists as a point of infinite density, surrounded by an event horizon with a radius of approximately 12 million kilometers, roughly 17 times the radius of our Sun, yet containing mass equivalent to more than 4 million solar masses compressed into a mathematical point of zero volume. As we drift peacefully toward this cosmic leviathan, the very fabric of space and time begins to curve dramatically under its immense gravitational influence, creating effects that transform our understanding of reality itself. The discovery of Sagittarius A star represents one of the greatest detective stories in modern astronomy. Beginning with the initial detection of intense radio emissions from the galactic center by Bruce Ballack and Robert Brown in 1974, followed by decades of patient observation that gradually revealed the true nature of this mysterious object. The asterisk symbol that distinguishes SGR A star from the larger radio source Sagittarius A was added in 1982 by Brown, who recognized that the strongest radio emission appeared to originate from a compact, non-thermal source embedded within the broader galactic center region. For many years, astronomers could only infer the presence of this massive dark object through its gravitational effects on surrounding stars and gas clouds, as the 25 magnitudes of extinction caused by intervening dust made direct optical observation impossible. The breakthrough came through infrared observations that could penetrate the cosmic dust, revealing individual stars whose rapid orbital motions around an invisible central mass provided the first direct evidence for the existence of a supermassive black hole at the heart of our galaxy. The event horizon. Telescope's historic first image of Sagittarius A star, released in May 2022, represents a triumph of human ingenuity and technological achievement, capturing the shadow of the black hole silhouetted against the glowing material in its accretion disk. This remarkable image, created by linking 8 radio observatories across 6 geographical sites to form a virtual telescope the size of Earth, reveals the characteristic ring-like structure predicted by general relativity, with a dark central region surrounded by a bright crescent of light from superheated gas spiraling toward the event horizon. The overall angular size of the source measures 51.8 microarcseconds as viewed from Earth, corresponding to a physical diameter of approximately 52 million kilometers at the black hole's distance of 26,000 light-years, creating an apparent size that would be equivalent to viewing a donut on the surface of the Moon from Earth. The processing of this image required 5 years of complex calculations to account for the rapid variability of the radio emission from SGR-A star, which fluctuates on timescales of minutes compared to the day-long stability of more distant black holes. The accretion rate onto Sagittarius A star proceeds at a remarkably modest pace for such a massive object, with only a few hundredths of an Earth mass worth of material falling into the black hole each year, a rate so low that our galactic center remains relatively quiet compared to the actively feeding supermassive black holes found in other galaxies. This sparse feeding regime results in what astronomers call a radiatively inefficient accretion flow, where the infalling material becomes extremely hot but radiates away most of its energy before reaching the event horizon, creating a tenuous, high-temperature plasma that glows primarily in radio and X-ray wavelengths. The low accretion rate also explains the absence of the powerful relativistic jets that characterize more actively feeding black holes, though recent observations have detected weak, collimated outflows that may represent the faint echoes of more dramatic activity that occurred in the recent past. Occasionally, larger amounts of material fall toward the black hole, creating flaring events that can be observed simultaneously across multiple wavelengths, providing insights into the physics of accretion and the structure of the magnetized plasma surrounding the event horizon. The spin of Sagittarius A star represents one of its most fundamental and fascinating properties, with recent measurements indicating that the black hole rotates at approximately 60% of the maximum possible rate allowed by the laws of physics, completing a full rotation in just a few minutes. This rapid rotation creates a phenomenon known as frame dragging, where the spinning black hole literally twists the fabric of space-time around it, forcing nearby matter and even empty space itself to rotate in the same direction as the black hole. The effect of this spin becomes visible in the shape of the ergosphere, a region outside the event horizon where space-time is dragged along so strongly that nothing can remain stationary relative to distant observers, creating a football-shaped distortion in the geometry of space and time. The measurement of black hole spin requires sophisticated analysis of the X-ray emission from the innermost regions of the accretion disk where general relativistic effects cause characteristic spectral features that carry information about the rotation rate and the warping of spacetime near the event horizon. The magnetic field surrounding Sagittarius A star creates an additional layer of complexity in this already exotic environment, with field strengths reaching thousands of times stronger than Earth's magnetic field, and organized into structures that channel the flow of charged particles and regulate the accretion process. The event horizon. Telescope observations have revealed that these magnetic fields exhibit surprisingly ordered patterns despite the turbulent and violent conditions near the black hole, creating spiral structures that bear remarkable similarity to those observed around the much more massive black hole in the galaxy M87. These magnetic fields play a crucial role in extracting rotational energy from the spinning black hole through the Blandford-Znajek mechanism, potentially powering the weak outflows and flaring activity observed from SGR-A star. The interaction between the magnetic field and the accretion flow also creates the conditions necessary for particle acceleration, generating the high-energy electrons responsible for the radio and X-ray emission that allows astronomers to study this otherwise invisible object. The gravitational field of Sagittarius A star creates conditions so extreme that they provide natural laboratories for testing Einstein's theory of general relativity in regimes that cannot be reproduced anywhere else in the universe. The famous S2 star, which approaches to within 120 astronomical units of the black hole during its 16-year orbit, experiences gravitational redshift effects so strong that its light is measurably shifted toward longer wavelengths when observed at closest approach. The star's orbital motion also exhibits relativistic precession, causing its elliptical path to slowly rotate in space at a rate that precisely matches Einstein's predictions for the curvature of spacetime around a massive object. These observations, along with similar measurements of other stars in tight orbits around SGR-A star, provide some of the most stringent tests of general relativity ever performed, and have confirmed Einstein's century-old theory with remarkable precision. The environment immediately surrounding Sagittarius. A star extends far beyond the physical boundary of the event horizon, creating a sphere of influence that shapes the dynamics of matter and energy across the entire central parsec of our galaxy. Within this region, the black hole's gravity dominates over all other forces, creating tidal effects so strong that they can disrupt molecular clouds, accelerate gas to relativistic velocities, and strip material from passing stars through spaghettification processes. The accretion disk itself extends outward from the innermost stable circular orbit to distances of several hundred Schwarzschild radii, creating a hot, magnetized plasma environment where temperatures reach hundreds of millions of degrees and magnetic reconnection events can accelerate particles to near light speed velocities. As our peaceful cosmic journey brings us to the very edge of this ultimate gravitational abyss, we stand at the threshold between the familiar physics of the everyday world and the exotic realm, where space and time themselves become players in the cosmic drama, where the ordinary concepts of past and future give way to the timeless geometry of curved spacetime, and where our galactic home reveals its deepest and most profound secret. As our peaceful cosmic journey reaches the most profound threshold in the universe, we approach the event horizon of Sagittarius A star, that mystical boundary where the familiar laws of physics as we know them transform into something far more extraordinary and fundamental. This invisible spherical surface, extending approximately 12 million kilometers from the black hole's center, represents the ultimate point of no return, where the escape velocity required to break free from the gravitational field equals the speed of light itself, creating a boundary beyond which nothing, not even light, can ever return to the outside universe. The event horizon exists not as a physical surface that could be touched or detected by a traveler crossing it, but rather as a mathematical boundary in spacetime, a coordinate where the very geometry of the universe shifts so dramatically that all future paths lead inexorably toward the central singularity. As we drift toward this cosmic threshold, time itself begins to behave in ways that challenge our everyday understanding, with the passage of moments becoming relative to our position and velocity in the increasingly curved spacetime surrounding the black hole. The phenomenon of gravitational time dilation creates one of the most fascinating and counterintuitive aspects of our approach to the event horizon, where time flows at different rates depending on how deep we venture into the black hole's gravitational well. From the perspective of a distant observer watching our journey from a safe location far from the black hole, our clocks would appear to tick progressively slower as we approach the event horizon, with each second stretching into minutes, then hours, then years, until our apparent motion comes to a complete halt at the boundary itself. This external observer would see us frozen at the event horizon for eternity, our image gradually fading and redshifting toward longer wavelengths as our light becomes increasingly difficult to detect, yet never actually witnessing our crossing of this cosmic boundary. However, from our own perspective, as infalling observers, our clocks continue to tick normally, and we would cross the event horizon in a finite amount of proper time, perhaps only a few minutes for a black hole of Sagittarius A's mass, experiencing no special sensation or dramatic change as we pass through this invisible threshold. The curvature of space-time near the event horizon creates a gravitational environment so extreme that it fundamentally alters the nature of causality and the possible directions that matter and energy can travel. Far from the black hole, particles and light rays can move in any direction through space, constrained only by the universal speed limit of light. But as we approach the event horizon, the warping of space-time gradually reduces the number of paths that lead away from the black hole. At the event horizon itself, this geometric constraint becomes absolute, with all possible future trajectories pointing inward toward the central singularity, making escape not just practically impossible, but geometrically forbidden by the structure of space-time itself. Inside the event horizon, the concepts of space and time become interchanged in a sense, with the radial direction toward the singularity becoming time-like rather than space-like, meaning that falling inward becomes as inevitable as moving forward through time in the ordinary world. The tidal forces generated by the immense gravitational field near the event horizon create another layer of exotic physics that would profoundly affect any material object attempting to cross this boundary. These tidal effects arise from the difference in gravitational acceleration between different parts of an extended object, with the side closer to the black hole experiencing stronger gravitational pull than the side farther away. For stellar mass black holes, these tidal forces become strong enough to tear apart any material object long before reaching the event horizon, in a process colorfully known as spaghettification. But for supermassive black holes like Sagittarius A star, the gentler gradient of the gravitational field allows objects to survive the crossing intact and experience spaghettification only deep inside the event horizon. A hypothetical astronaut falling into our galactic center black hole would remain structurally intact while crossing the event horizon, only beginning to experience the stretching effects of extreme tidal forces as they approached within a few thousand kilometers of the central singularity. The quantum mechanical aspects of event horizon physics introduce additional layers of mystery and ongoing scientific debate about the true nature of these cosmic boundaries. Stephen Hawking's revolutionary prediction that black holes emit thermal radiation through quantum fluctuations near the event horizon suggests that these boundaries are not perfectly absorbing surfaces, but rather dynamic regions where virtual particle pairs are constantly being created and destroyed. Some of these virtual particles fall into the black hole, while others escape to infinity, creating a net outward energy flow that causes the black hole to slowly evaporate over cosmic timescales, with the radiation temperature being inversely proportional to the black hole's mass. For a supermassive black hole like Sagittarius A star, this Hawking radiation is extraordinarily faint, with a temperature of only about 10 to the minus 8 Kelvin, far colder than the cosmic microwave background, meaning that our black hole is currently growing by absorbing cosmic background radiation faster than it loses mass through Hawking evaporation. The information paradox represents one of the most profound puzzles in modern theoretical physics, questioning what happens to the information contained in matter that falls past the event horizon. Classical general relativity suggests that information falling into a black hole is lost forever, destroyed when the black hole eventually evaporates through Hawking radiation. But quantum mechanics demands that information must be conserved in any physical process. This fundamental conflict between two of our most successful physical theories has generated decades of intense research and debate, with proposed solutions ranging from the idea that information is somehow encoded in the Hawking radiation to more exotic possibilities such as the existence of wormholes or the holographic principle, which suggests that all the information falling into a black hole is actually stored on its two-dimensional surface. Recent theoretical work has explored the possibility that the event horizon itself might have a more complex structure than previously thought, potentially possessing quantum hair or other properties that could preserve information while still maintaining the essential characteristics of a black hole. The recent observations from the Event Horizon Telescope have provided unprecedented insights into the actual behavior of matter near the event horizon, revealing the bright ring of glowing plasma that surrounds the black hole's shadow, and confirming many of the predictions of general relativity about the appearance of these extreme objects. These observations show that most of the observable emission comes from material just outside the event horizon, where gas spiraling into the black hole is heated to billions of degrees and accelerated to significant fractions of the speed of light. The shadow cast by the event horizon appears as a dark central region surrounded by the brilliant photon ring, created by light rays that have circled the black hole multiple times through gravitational lensing effects before escaping to reach our telescopes. The size and shape of this shadow provide direct measurements of the black hole's mass and spin, while the temporal variability of the emission reveals the chaotic dynamics of the accretion flow in the strong gravitational field regime. As our consciousness approaches the event horizon of Sagittarius A star in this peaceful cosmic meditation, we stand at the ultimate frontier of human knowledge. where the familiar concepts of space, time, causality, and information encounter their most extreme test. The event horizon represents not just a boundary in space, but a boundary in our understanding of the universe itself, where the classical physics that governs our everyday experience gives way to the exotic predictions of general relativity and quantum mechanics. Beyond this threshold lies a realm that no observer can ever report back from, a region of space-time so fundamentally different from our normal experience that it challenges the very concepts we use to describe reality. Yet in contemplating this cosmic boundary, we touch something profound about the nature of existence itself, recognizing that even the most extreme environments in the universe operate according to mathematical principles that human minds can comprehend, even if they cannot directly experience them. As we prepare to cross this ultimate threshold in our imaginary journey, we carry with us the peaceful understanding that the universe, in all its mystery and wonder, remains fundamentally knowable through the patient application of scientific observation and theoretical understanding. As our peaceful cosmic journey continues beyond the event horizon of Sagittarius A star, we enter a realm where one of the most profound mysteries in modern physics reveals itself: the black hole information paradox, a puzzle so fundamental that it challenges our deepest understanding of how reality itself operates at its most fundamental level. This paradox emerges from the apparent conflict between two of our most successful theories of physics: quantum mechanics, which demands that information must be conserved in any physical process, and general relativity, which seems to suggest that information falling into a black hole is lost forever when the black hole eventually evaporates through Hawking radiation. The paradox was first articulated by Stephen Hawking in 1974, when he discovered that black holes emit thermal radiation, leading to the startling conclusion that these cosmic giants slowly shrink over time, taking with them any information that ever crossed their event horizons. For nearly 5 decades, this puzzle has captivated the greatest minds in theoretical physics, generating thousands of research papers and spawning entirely new approaches to understanding the nature of space, time, and information in the universe. The essence of the information paradox lies in the fundamental principle of quantum mechanics known as unitarity, which states that the total amount of information in the universe must remain constant over time, even as it is transformed from one form to another. In the everyday world, this principle manifests in seemingly mundane ways. When you burn a book, the information contained in its pages is not destroyed, but merely converted into the arrangement of atoms in the smoke and ash, and in principle, with perfect knowledge of every particle's position and momentum, the original text could be reconstructed. However, when matter falls into a black hole, classical general relativity suggests that this information disappears from the observable universe forever, hidden behind the event horizon, where no signal can ever escape to tell us about its fate. When the black hole eventually evaporates through Hawking radiation, which appears to be completely thermal and random, the information seems to vanish entirely, violating one of the most cherished principles of quantum mechanics. The thermal nature of Hawking radiation creates the heart of this cosmic puzzle, as this emission appears to carry no information about the matter that originally fell into the black hole, resembling instead the random thermal glow of a perfect blackbody radiator. Hawking's original calculation showed that the radiation temperature depends only on the black hole's mass, with smaller black holes radiating more energetically than larger ones, but the radiation itself carries no signature of what created the black hole or what has fallen into it over its lifetime. For our galactic center black hole, Sagittarius A star, with its mass of 4.3 million solar masses, the Hawking temperature is extraordinarily cold, approximately 1.5 times 10 to the minus 8 Kelvin, making the radiation so faint that it would take longer than the age of the universe to detect even a single photon. However, the principles involved remain the same regardless of the black hole's size, and the paradox persists whether we consider stellar mass black holes that might evaporate in 10 to the 67th years, or primordial black holes that could disappear much sooner. Recent developments in theoretical physics have suggested several potential resolutions to the information paradox, each offering different insights into the fundamental nature of reality. The AD/CFT correspondence, discovered in 1997, provides one of the most promising approaches by establishing a mathematical equivalence between theories of gravity in curved spacetime and quantum field theories without gravity. This remarkable duality suggests that information falling into a black hole in the gravitational theory corresponds to information that remains accessible in the equivalent quantum field theory, implying that information is preserved but encoded in subtle correlations within the Hawking radiation that become apparent only after long time periods. In 2019, physicists made significant progress by calculating the entropy of Hawking radiation more carefully, showing that the radiation eventually becomes entangled with the black hole interior in a way that allows information to escape while maintaining the overall consistency of quantum mechanics. The holographic principle offers another fascinating perspective on the information paradox, suggesting that all the information contained within a volume of space can be encoded on its two-dimensional boundary. Applied to black holes, this principle implies that the information falling past the event horizon is actually stored on the black hole's surface, where it remains accessible to outside observers through the subtle properties of the Hawking radiation. This idea leads to the startling conclusion that what we perceive as a three-dimensional interior of a black hole might actually be a holographic projection of information encoded on its two-dimensional event horizon, fundamentally altering our conception of space and the nature of physical reality. The holographic principle has found support in various areas of theoretical physics and has led to new insights into the relationship between geometry, gravity, and quantum information. Quantum error correction has emerged as another powerful tool for understanding how information might be preserved in black hole evaporation, drawing parallels between the physics of black holes and the techniques used to protect quantum information in quantum computers. In this framework, the black hole interior and its Hawking radiation form a quantum error-correcting code, where the information about infalling matter is redundantly encoded across multiple degrees of freedom in a way that allows its recovery even when some parts of the system are inaccessible. This approach suggests that the apparent randomness of Hawking radiation is actually an illusion created by our limited ability to access all the relevant information, and that with sufficiently sophisticated measurements, an external observer could in principle reconstruct the information about everything that ever fell into the black hole. The firewall paradox represents another layer of complexity in our understanding of black hole interiors, challenging the assumption that crossing the event horizon is a smooth, uneventful experience. Proposed in 2012, this paradox suggests that maintaining both the equivalence principle of general relativity and the unitarity of quantum mechanics might require the existence of a highly energetic firewall at the event horizon that would incinerate any infalling observer. This dramatic proposal highlights the deep tensions between our understanding of gravity and quantum mechanics in extreme environments, suggesting that one of our fundamental principles about the nature of spacetime might need to be modified. The firewall paradox has sparked intense debate and has led to various proposals for resolving the conflict, including modifications to quantum mechanics, alterations to general relativity, or fundamental changes in our understanding of the nature of spacetime itself. Loop quantum gravity offers yet another approach to the information paradox by proposing that the classical singularity at the center of a black hole is replaced by a quantum bounce that eventually leads to the formation of a white hole. In this scenario, information falling into the black hole is not destroyed, but rather emerges from the white hole after a finite proper time, though this emergence might be delayed by enormous periods as measured by external observers. These remnant scenarios suggest that information does not escape gradually through Hawking radiation, but rather remains trapped within the black hole until the final moments of evaporation, when it is released all at once. While these models provide potential solutions to the information paradox, they also raise new questions about the nature of spacetime at quantum scales and the ultimate fate of matter in the universe. As our consciousness drifts deeper into the mystery of the information paradox during our journey through Sagittarius A, we encounter the profound realization that this puzzle represents more than just an academic exercise. It strikes at the very heart of our understanding of reality itself. The resolution of this paradox will likely require a fundamental revolution in our understanding of space, time, gravity, and quantum mechanics, comparable to the insights that led to the development of general relativity and quantum mechanics themselves. The journey toward understanding what happens to information in black holes has already yielded unexpected insights into the nature of entanglement, the holographic principle, and the deep connections between geometry and information, suggesting that the ultimate resolution of this paradox will illuminate aspects of the universe that we have not yet even begun to imagine. In contemplating these deep mysteries as we drift through the event horizon of our galaxy's central black hole, we touch upon questions that probe the very foundations of existence, recognizing that even in the most extreme environments in the universe, the quest for understanding continues to drive human consciousness toward ever greater insights into the nature of reality. As our peaceful cosmic meditation reaches its deepest contemplation within the event horizon of Sagittarius A, we arrive at the profound understanding that this supermassive black hole serves as far more than just a cosmic endpoint. It functions as the galactic engine, the beating heart that has shaped and continues to influence the entire evolution and structure of our Milky Way galaxy across billions of years. The gravitational influence of our central black hole extends far beyond its immediate vicinity, reaching across the entire galaxy through mechanisms both subtle and dramatic, regulating star formation rates, controlling gas flows, and maintaining the delicate balance between growth and stability that has allowed our galaxy to persist as a coherent structure for over 13 billion years. Recent theoretical breakthroughs in understanding the black hole information paradox, including advanced quantum error correction approaches and the recognition of nonviolent non-locality effects, suggest that information is indeed preserved through mechanisms we are only beginning to comprehend, with quantum correlations creating subtle signatures in the very fabric of spacetime that surrounds the event horizon. These discoveries indicate that black holes like Sagittarius A star may serve as cosmic information processors, encoding and preserving the complete history of everything that has ever fallen into them, while simultaneously influencing the galaxy's evolution through their gravitational and electromagnetic effects. The role of Sagittarius A star as a galactic regulator becomes apparent when we consider how its gravitational field shapes the large-scale structure and dynamics of the entire Milky Way system. The supermassive black hole's influence extends through the galactic bar structure, creating orbital resonances that channel gas from the outer spiral arms toward the galactic center while simultaneously preventing too rapid an accumulation of material in the nuclear regions. This delicate balance maintains the galaxy in a state of controlled evolution, where star formation proceeds at rates that allow for the gradual enrichment of the interstellar medium with heavy elements while avoiding the catastrophic starbursts that could consume all available gas in a few 100 million years. The black hole's periodic episodes of enhanced activity, possibly triggered by the infall of gas clouds or the disruption of stars that venture too close, generate powerful outflows that can sweep through the galactic center region, clearing out accumulated gas and temporarily suppressing further star formation. These feedback cycles operate on timescales of millions to tens of millions of years, creating a self-regulating system that has maintained the galaxy's overall stability throughout cosmic time. The magnetic field structure emanating from Sagittarius A star creates another layer of galactic influence that extends far beyond the immediate vicinity of the black hole. Recent observations have revealed that the magnetic field lines threading through the galactic center region connect to larger-scale field structures that permeate the entire galactic disk and halo, creating a unified magnetic architecture that influences the behavior of cosmic rays, the formation of molecular clouds, and the propagation of stellar winds throughout the galaxy. This galactic magnetic field, partially organized and strengthened by the rotation of the central black hole through magnetohydrodynamic processes, serves as an invisible scaffolding that helps maintain the spiral arm structure and guides the flow of ionized gas between different regions of the galaxy. The interaction between this organized magnetic field and the turbulent motions of the interstellar medium creates conditions that can either enhance or suppress local star formation, providing another mechanism through which the central black hole influences galactic evolution on vast scales. The recent resolution of aspects of the black hole information paradox through quantum error correction theory and the recognition of space-time entanglement offers profound new insights into the nature of black holes as cosmic information processors. The latest theoretical work suggests that the information falling into Sagittarius A star is not lost, but rather encoded in quantum correlations that exist between the black hole interior and the surrounding spacetime, with these correlations creating subtle but detectable effects in the gravitational wave signatures and electromagnetic emissions from the galactic center region. This non-violent non-locality, as it has been termed, implies that the black hole serves as a quantum memory bank that preserves the complete history of our galaxy's evolution, storing information about every star that has ever fallen past its event horizon, every gas cloud that has been accreted, and every cosmic event that has occurred in its gravitational sphere of influence. The emerging understanding of spontaneous symmetry breaking in black hole systems suggests that the radiation emitted by Sagittarius A star may carry encoded information about its interior state, though detecting and decoding this information requires technologies and theoretical frameworks that are only now beginning to emerge. The long-term evolution of Sagittarius A star and its relationship with the galaxy presents a cosmic story that unfolds over timescales almost incomprehensible to human experience. Over the next several billion years, the black hole will continue to grow through the gradual accretion of gas and stellar material, though at the current modest rate, it would take longer than the age of the universe to double its mass through accretion alone. More dramatic growth episodes may occur if our galaxy experiences major mergers with other large galaxies, particularly the anticipated collision with the Andromeda Galaxy in approximately 4 billion years, which could funnel vast amounts of gas toward the galactic center and temporarily transform Sagittarius A star into a much more active and luminous object. The eventual fate of the black hole, assuming the universe continues to expand and cool, involves the incredibly slow process of Hawking evaporation, which for an object of Sagittarius A's mass would require approximately 10 to the 87th power years to complete, a time span so vast that the universe itself may undergo fundamental changes in its basic structure before this process reaches completion. The implications of viewing Sagittarius A star as a galactic engine extend to our understanding of how supermassive black holes throughout the universe influence galaxy formation and evolution on cosmic scales. The feedback mechanisms operating in our galactic center provide a template for understanding how similar processes shape galaxies across the observable universe, from the smallest dwarf systems to the largest elliptical giants. The correlation between black hole mass and the properties of their host galaxy bulges, known as the M-sigma relation, suggests that the growth of supermassive black holes is intimately connected to the formation of galactic structures, with the black holes serving as both products and drivers of galactic evolution. This co-evolution between black holes and galaxies represents one of the most fundamental processes in cosmic evolution, determining how matter assembles into the large-scale structures we observe today, and influencing the formation of stars, planets, and ultimately the emergence of conditions suitable for the development of life. The quantum information aspects of black hole physics suggest that Sagittarius A star may preserve information not just about our galaxy's past, but about the fundamental nature of space, time, and reality itself. The holographic principle implies that all the information contained within the three-dimensional volume surrounding the black hole is encoded on its two-dimensional event horizon surface, creating what amounts to a cosmic library that stores the complete quantum state of everything that has ever interacted with the black hole. Recent advances in understanding quantum error correction in black hole physics suggest that this information is not only preserved, but can in principle be recovered, though the practical challenges of extracting and decoding such information using any conceivable technology remain formidable. The recognition that black holes operate as quantum computers of sorts processing and storing information through mechanisms that obey the fundamental laws of quantum mechanics while simultaneously shaping the large-scale structure of the universe through their gravitational influence, represents a profound synthesis of our understanding of the quantum and cosmic realms. As our consciousness completes this extraordinary journey through the heart of our galaxy, we carry with us the profound realization that Sagittarius A star represents far more than just an exotic endpoint of stellar evolution. It stands as the central organizing principle of our cosmic home, the galactic engine that has shaped the conditions allowing for the emergence of stars, planets, and life itself throughout the Milky Way. The peaceful understanding that emerges from this cosmic meditation reveals that even the most extreme objects in the universe serve essential roles in the grand symphony of cosmic evolution, operating according to physical laws that human minds can comprehend and appreciate even when direct experience remains forever impossible. The journey to the center of our galaxy ultimately brings us back to ourselves, to our place as conscious observers in a universe of extraordinary beauty and complexity, where supermassive black holes serve not as destroyers, but as architects of the cosmic structures that make our existence possible. If this cosmic journey has sparked your curiosity about the universe and left you with a sense of wonder about our place in the cosmos, make sure to subscribe to the Sleepy Cosmos and hit that notification bell so you never miss our explorations of the most amazing phenomena in space and time as we continue to venture into the deepest mysteries of our extraordinary universe.